Hi everyone, this is going to be the presentation for flood prediction. This is going to be a little weird at first. Maybe it's going to be a little bit weird for the entire time, but we're going to get through this and we'll figure out a way. So when we're talking about flood prediction and how bad floods are going to get, we need to keep in mind this idea of a recurrence interval. And so you need to remind yourself what the equation and the definition for a recurrence interval is. And so you might want to start thinking about, what we mean by recurrence interval. What's the equation for calculating a recurrence interval? And so at the most basic level, for floods, the recurrence interval is going to be t is equal to n plus 1 divided by m. And so it's not a very hard equation, and the math is fairly straightforward. The t is the recurrence interval. The n is the number of years that you have in your record, and that's of peak annual flow. So how many years you have in each for your river and how many annual years you have for that. M is then the magnitude. And so that's your magnitude. And so your magnitude is then number 1 is the largest flood. Number 2 is the second largest flood, and so on. And so you're going to rank those. And then you can come up with the recurrence interval for these different sizes. And so just as a reminder, we had a small data set that looks something like this, where we had year, and we had a couple years worth of data. And then we had the discharge, the peak annual discharge that happened in that year. So that's peak. And so let's just come up with some numbers here. Let's say it was that. And then we're going to go with this. And so that's the peak. Okay. So then we're going to rank these by M. And so you're going to put M, the number 1 for the largest flood, number 2 for the second largest flood, and so on. You're also then going to have to figure out what n equals. I'll jump ahead and give you that one. Since we have 4 years worth of data, n equals 4. So then n plus 1 is going to equal 5. So if you want to pause here, you can calculate m. And so there's our m, 1, 2, 3, 4. All right, if we're going to calculate t then, t is going to be equal to the equation n plus 1 over m. So n plus 1 is going to equal to 5, and so it's going to be 5 divided by each of these. So it's going to be 5 thirds, or 5 over 2, or 5 over 1, or 5 over 4, which just equals, what, 1.67, 2.5, 5, and 1.25. I feel a little nervous making these calculations without all of you to check my math for me. At least in real time, I'm sure you're checking my math over the time. And so this gives us an equation for, and some data for recurrence intervals. And so, if you want to know what the 5-year flood is, well, then it's going to be this one. It's going to have a discharge of about 247, probably this is units if these are coming from the United States government, of cubic feet per second. So those are our calculations for flood prediction. Now, if we want to take that and do something with it, you remember that the flood that has the most important values for things like flood insurance and flood regulation is the 100-year flood. And so if the 100-year flood is what we're trying to calculate, my question to you is, how much data do we need for that? How many years worth of data do we need to calculate the 100 years flood? If I had multiple choice questions, that would be a pretty good multiple choice question. The answer is that you only need 99 only years of data. And that's because of that equation n plus 1 over m. And so if n was 99, n plus 1 would be 100, and then the largest one would be, in your ranking, would be 1. So 100 divided by 1 equals 100. So you need 99 years worth of data. And we talked about in class how if you want to calculate this graphically, what you do is you put recurrence interval on the horizontal axis and you put river discharge on the vertical axis, and you can start plotting these. And so you get some data that looks maybe something like this. And so, if you want to put numbers on here, you could put 5 years, 10 years, 50 years, etc. And we can extend that axis out a little bit and make that 100. Yes, this axis is not linear, it's logarithmic, but we don't have to deal with that right now. And so a mathematician would say, well, gosh, you could just take this line and extend that line all the way out, and you can go as far as you want, just using a general equation for a line, y equals mx plus b, we can extend that line all the way out. And so then you could take that line and extend it out to 100 and then go across and get a rough idea of what it might be for the 100-year flood. So that's great and all, but we technically don't do that. Typically what we have is we have a set of data and we extrapolate out. Now, there's a couple of dangers here. If you have too few data, you only have a few years worth of numbers, well then by extrapolating out, you're going to get really fuzzy answers and you're not going to have a very certain result. You should use at least 30 years worth of data at a minimum in order to do this. That's the same as if you're talking about climate change. You're going to need about 30 years worth of data. But what if you have too many? Here in New Jersey on the Passaic River, there are more than 100, it's about 120, 130 years worth of data that we can go back and find peak annual discharge for. And the problem with that is that while it might seem great, you have all these years to work with, you might have some changes in conditions that lead to the floods. And so these changes in conditions, that's a G, sorry, could include things like climate. They could include things like land use. Over really long timescales, you might get things like changes in mountain ranges, changes in vegetation. That's connected to land use. But all those things would give you different variables in terms of what these floodings were. So if you were using 100 years worth of data and looking at this kind of chart and plotting all those, well, then you'd be using river data from 1900, 1901, 1902, 1903, etc. And that's for the Passaic River. And gosh, think how things have changed in the Passaic River since 1900. Climate's changed. There's many more people, many more impervious surfaces in there. And so those are all things that we need to consider if we're going to take that into consideration. All right, so that's our presentation on predicting floods and trying to calculate things like the 100-year flood. Let me know if you have questions. Thanks.